I want you to do something for me. Just imagine picking up a rock. You know, any old rock from your backyard. Hold it in your hand, feel how heavy it is, how cold. Well, it's about as boring as it gets, right? But what if I told you that plain, simple rock is hiding a secret?
And no, that's not just some fancy poetry. That is physics. Inside every single atom of that rock, there is a fire with an almost unimaginable power. And it's not just in the rock. It's in your glass of water, it's in the grass outside, it's in every bone in your body. That fire is there.
You know, those two simple questions, they lead us to one of the most profound and frankly disturbing discoveries in the history of science. It's a discovery that doesn't just change what we know about the world, it changes what the world is. To really get it, we've got to go on a little journey, right to the heart of matter itself.
Okay, so to find this hidden fire, we have to shrink ourselves down. I mean, way, way down, past what any microscope could ever hope to see. We need to enter the world of the atom. And the very first thing you'd notice when you got there is, well, nothing. And that is shock number one. The solid, dependable world that we all trust, it's basically an illusion. Matter is almost entirely a void. Now, it's really hard to wrap your head around just how empty we're talking, so let's try an analogy.
Let's blow up an atom to the size of a giant football stadium. Okay? You're standing in the middle of this huge, empty stadium. Now, where's all the stuff? The entire mass of that atom would be in a nucleus the size of a single marble, sitting right there on the 50-yard line. The rest is just empty space, with a few tiny electrons zipping around like gnats. The real action, the source of that incredible fire, it's all happening inside that tiny little marble.
See, inside that tiny, impossibly dense nucleus, there is a war raging, a constant, violent battle between two of the universe's most fundamental forces. And this battle, it determines everything. It's why stars shine, it's why bombs explode, and it's why you and I even exist at all.
So, on one side, you've got the electromagnetic force. Let's call it the pusher. All the positive protons inside that nucleus are being pushed apart by this force. They desperately want to fly away from each other. But then you have the strong nuclear force. We'll call it the grappler. It's unbelievably strong. But here's the catch. It has a super short reach. It can only grab onto particles that are right next to it. And right there, that's where the trouble starts. In a small, tidy nucleus, all the particles are huddled together, so the grappler easily wins. But in a big, bloated nucleus, like uranium, you've got protons on opposite sides of the room, so to speak. The grappler can't reach that far, but the pusher can. So the whole nucleus gets wobbly, unstable, quivering like a drop of water about to break apart. So, if these really big atoms are so unstable, what does nature want to do about it? Well, just like a ball on a hill, it wants to roll down to a more stable, more comfortable state. And the rules for this whole process are governed by something called binding energy.
The easiest way to think about binding energy is to picture it as glue. It's the energy that holds the nucleus together. And the more glue you have per particle, the more stable and solid the atom is. Nature is always trying to arrange things to get the most glue possible. This whole setup creates a sort of energy landscape, a landscape of stability. And right at the very bottom, in the deepest, most stable part of this valley, sits iron. Iron has the most binding energy per particle. It's the most stable element. And in a way, everything else in the universe wants to become iron. So there are two ways to roll down into this valley of stability. On one side, you've got light elements like hydrogen that can slam together and combine. That's fusion. It powers our sun. But on the other side of the valley, you have the heavy, unstable elements like uranium. They can split apart to get closer to iron, and that's fission. That right there is the fire in the rock. So let's zoom in on that moment. On fission, on the fire in the rock. What actually happens in that one infinitesimal instant when that wobbly uranium nucleus finally lets go and tears itself apart? I mean, the numbers here are just mind-bending. This whole event is over in less than 100 billionth of a trillionth of a second. It starts when a slow neutron just wanders into the nucleus, and that's the last straw. The nucleus starts to wobble and stretch, a waste forms where the grappler force is losing its grip, and then, snap, it ruptures. And what comes flying out of this tiny explosion? Well, you get two brand new, smaller atoms, like barium and krypton. You get a couple of stray neutrons, and you get a huge blast of pure energy in the form of gamma rays. But this brings up a really profound question. Where did all that energy actually come from?
Okay, this is the part of the story that really changes everything. Because if you could somehow take all the pieces from before the split and all the pieces from after and weigh them with perfect precision, you would find something that seems totally impossible.
About 0.1% of the total mass is just gone, vanished. Matter, the very stuff of the universe, has simply ceased to exist. So where on earth did it go? Well, the truth is, it didn't go anywhere. Einstein's famous equation holds the secret. That missing mass wasn't lost. It was converted directly into pure energy. You see, mass and energy aren't two different things. They are two faces of the exact same coin. And the exchange rate, that c² part, the speed of light squared, is absolutely colossal.
Just let that sink in for a second. We're not even talking about fission here, we're talking about the total energy that is locked away inside of matter itself. If you could take a single raisin and convert it completely to energy, it would release the same destructive force as a nuclear weapon. That's the power that is hiding inside every single object you see around you.
So, once we figured this out, once humanity learned how to actually unlock that fire, it changed our world forever. It changed how we can power our civilizations and how we can destroy them.
Remember those few stray neutrons that fly out when an atom splits? Well, they can go on to hit other uranium atoms, causing them to split, which releases more neutrons, which hit more atoms, and on and on. It's an exponential chain reaction. If you just let it run wild, you get a nuclear bomb. But if you control it carefully so that each split triggers just one more, you get a nuclear reactor. The physics is exactly the same. The choice is ours. And this all leads us to the ultimate philosophical shock. The solid floor you're standing on, it's not really solid. It's energy, a vast, staggering amount of energy that's been frozen into a temporary pattern, held in this delicate truce between cosmic forces.
So where did this energy even come from in the first place? It was forged in the heart of a supernova. Every heavy atom like uranium was created in the explosive death of a massive star billions of years ago. The energy it holds inside it is the leftover fire from that cosmic cataclysm.
So let's go back to that rock. That simple, boring rock. It's not just a rock, is it? It's a relic from a dead star. It's a storehouse of unimaginable energy. It is frozen fire. And you know what? So are you. The question is, now that you know, does the world feel any different in your hands?